All right, well, hello again. My name is Georgy. I'm with MidWest Optical Systems. We're located in Chicago, Illinois, or rather Palatine, Illinois, just a few minutes outside of Chicago. It's really good to be here with all of you virtually. And today I'm going to be talking about how you can help improve your machine vision image quality with optical filters. You may have different experiences with optical filters. You might be extremely experienced, you know exactly which one to choose, and you might know all about it. You might be somewhere in the middle, or you may never have any experience with optical filters at all. And so regardless of where you are with optical filters and your experience with them, my hope is just to show you some different kinds of filters, different applications, and how image quality can be improved or increased. And hopefully you walk away with some tips and tricks and just a better understanding of optical filters in general. Kind of the main goal for today is to help you understand that optical filters are a necessity and not just an accessory. That's kind of the mantra, the slogan that we all live by here at MidWest Optical. Filters are really a passion for us, and filters really focused on machine vision. This is kind of the hope for today, to let you know that filters are a necessity, not just an accessory. So before we jump in, I just want to go over a couple of key terms that you may or may not be familiar with. This right here is something called a transmission curve. This accompanies every filter that you're looking at. This lets you know how the filter is going to perform. Pretty much what filters do is help to block certain wavelengths of light and pass other ones. So blocking and passing, it's filtering light, and that's what it's kind of in charge of doing. This is a transmission curve, and along the x-axis here, we have the spectrum of different wavelengths. If you're familiar with this already, of course, we have the UV, the visible, what our eyes are seeing, what human eyes are seeing, and to the right, we have the infrared, and there's different bands of infrared. There's near infrared and mid-range and long range and short SWIR or shortwave infrared. And then along the y-axis here, we have the transmission. This refers to how much of a particular wavelength is being allowed through. So this curve here, this pass band, which will look different, depending on which filter you're going to be looking at. This pass band lets me know how much of a particular wavelength is being allowed through. So if you've heard of a band pass filter, the reason it's called a band pass filter is because it has a pass band. Again, how high that it is on the curve, the transmission, refers to how much of that particular wavelength is being allowed through. So a filter that has a very high transmission in the 550 wavelength area is doing a good job of transmitting all of that area, of that wavelength region. And then out of band is what's being blocked. So if I refer to a filter, or if you hear a filter having very good out of band blocking in the infrared or the IR, that just means that that filter is doing a good job of blocking infrared, which may not be required in your application. The full width half max, or the FWHM, refers to how wide that pass band is. So how much of how large of an area of that wavelength region is being passed through. So if you are using an LED light source and you're using a filter to pass the LED and block ambient light, you want something that's a little bit wider, because LED output is a wider output. If you're using something like a laser, you might want something narrower. So how wide or narrow that pass band is referred to the full width half max. So again, this is a transmission curve, and this lets you know how a filter is going to perform. Now, filters are useful for lots of different things. They can help with contrast, improve resolution, ensure repeatability. Polarizing filters help to reduce glare. They can help with color correction and achieving natural color rendition. And also they can help with protection too. They can also protect your lens and your camera from damage. So let's take a look at a few different filters and see how how they're essential for each of these things. I mentioned how filters can help with contrast. And typically with machine vision, contrast is the name of the game. You're trying to create contrast so that your system has an easier time picking something out from the background or telling two colors apart, reading a barcode. You're trying to create contrast so the system can read something. Now here in this original color image with these red and blue caps, you can see that there's plenty of contrast. It's very easy to tell the red from the blue apart. But what if you had a monochrome system and a non-color system? Well, without a filter, it's more difficult to tell the red and the blue apart. But here I'm using a red bandpass filter. And what's happening is that the red wavelengths are being passed, as you can see in this little chart right here. The red wavelengths are being passed and the blue wavelengths are being blocked. So what's happening is that when you pass a wavelength in a monochrome system with a bandpass filter, the wavelengths that you're passing become highlighted and wavelengths that you're blocking become darkened. Okay, it's an important thing to remember, especially when you're using filters in a monochrome setting, bandpass filters. When you pass a wavelength, it becomes highlighted, blocking darkens. I'm essentially doing the reverse here with the blue bandpass filter. I'm passing the blue wavelength, so the blue caps are being highlighted, and then I'm blocking. Remember from the transmission curve, the out of band blocking on the red is good. It's blocking the red, and so all the red caps are darkened. Okay, so filters are very good for helping to create that contrast, and bandpass filters are really essential, if you're working with the monochrome system. Filters are also really great at helping to increase resolution. This is an added benefit that you might not know about. Something called chromatic aberration is a type of distortion that occurs in lenses. This happens because lenses try to focus different wavelengths at the same focal point. And because different wavelengths have different refractive indexes, they bend differently. The lens has a difficult time trying to focus all that at the same point. And so what happens is you lose some focus, you lose some resolution, you lose some sharpness as displayed in this image of the target here. But if you only cared about a certain color or a certain wavelength, you can limit the number of incoming wavelengths by using a filter. A filter would filter out the wavelengths that you're not really interested in, whether it be ambient or other wavelengths, and just pass the intended wavelength. So here, I'm filtering everything out and they're just passing the blue wavelength. You can see that the lens doesn't have that chromatic aberration effect or distortion happening to it, and you can gain some resolution here, improve the resolution, as you can see the difference between these two example images here. So you can see that there's much higher resolution, brighter, clearer, sharper. So increasing contrast, increasing resolution. The last kind of thing about this of the beginning series here is how filters can really help you achieve repeatability, all right, or improve repeatability. We call filters an inexpensive insurance policy because they help to ensure that the application is going to work regardless of the environment. And what I mean by that is oftentimes you're setting up an application in often what looks like this first image, in a room that looks like this first image where there's no windows, lighting conditions are ideal, everything is controlled, you get the application working just right, and you're good to go. And then you move the application to the customer site or to your factory floor, or maybe you're rolling this out worldwide to lots of different sites. And all of a sudden you start getting read errors, or the application is not working like you expected it to. Well, what happened is that there's all this ambient light, interfering light. There's light from the skylights, there's light from windows, there's different reflections from people walking around constantly. Now, you have a couple of different solutions. You can turn off all the lights, which is really not a solution because there's people working there. You can build a giant shroud to shroud the whole and encase the whole application, but that's not a very good solution either. Your ideal solution is to put a filter. And the thing is, if you had used a filter from the application in the lab, if you used a filter in this first stage here, you'd already be controlling the light that's going into the system and the light that's being blocked. And so, using a filter from the very get-go is going to ensure that application is going to work regardless of the ambient lighting conditions that you were or were not aware of. So that's an important thing to keep in mind. Use a filter. You're already controlling the light regardless of the environment. So repeatability is improved when you use optical filters. In addition to bandpass filters and that we mentioned earlier, there's lots of different kinds of filters. I just want to go over a few here that are most commonly used in machine vision applications. Short pass, long pass. Acrylic is not so much a filter as it is a type of material that we use to make filters, but we have some acrylic options as well. Polarizers, neutral density, multi-band pass. And we'll go over each of these and look how they look at some different applications and see how they can work in your various use cases. Short pass filters, like the name implies, they help to pass shorter wavelengths and block longer ones. If you remember from this slide, the transmission curve, typically on a spectral curve here, or on a transmission curve, we refer to kind of the left side as the shorter wavelengths. That's the UV and the visible, and then the right side, the infrared wavelengths, we refer to as longer wavelengths. So shorter and longer. So when it comes to short pass filters help to pass shorter ones and block longer wavelengths. These are also called IR cut filters, if you're familiar with that. And they're typically included on color cameras, but lots of times in machine vision systems, they're removed or they're not included and you have to supply your own. Now, short pass filters, when you're dealing with a color application, is very good at helping to achieve natural color rendition. Now, in this application, on the left, we had a customer who set up several color cameras, at a football stadium. And when you're looking at the image, there was this weird pink red hue, on the image, and it was confusing because obviously, to a human eyes, it looked fine. What was happening was the camera was picking up on the infrared from the sunlight and from the stadium lights. And causing this, unnatural color rendition. While using a short pass filter, again, passing the visible wavelengths that our human eyes are used to and blocking infrared wavelengths, you can see in this right image how it helps to improve that natural color rendition. Short pass filters are also very useful for helping to prevent laser damage, especially if you're using an IR laser laser wavelengths are in the IR. They help to protect your lens and your camera from in a laser inspection application where you might be monitoring a laser marking application. So you're just monitoring what happens, and it's possible some stray laser beams can damage your sensor and your lens. And so a short pass filter is good for blocking those infrared lasers, but allowing you to still see your applications because it's passing visible. Now, when selecting a short pass filter for this type of application, you want to make sure that you get an absorbative type filter. This will help to absorb your energy instead of reflecting it into another camera system or into somebody else's eyes. So short pass filters are great for helping to achieve natural color rendition, and then also helping to prevent laser damage to your lens and camera in laser inspection or kind of applications. As we continue, long pass filters kind of do the opposite of a short pass filter. They help to pass the longer wavelengths and block the shorter ones. We don't use a ton of these in machine vision, but it does happen from time to time. Long pass filters are very useful when you're trying to image in the near IR with a standard digital CCD sensor. Standard sensors are not very sensitive in that near IR, but what you can do is you can use a long pass filter to kind of increase that efficiency in the small area that sensor is sensitive. So you can test out applications in the IR like this one I'm doing here with these water bottles filled with water, and they're clear. I'm using an infrared light source to illuminate, and you can see that using the long pass filter, I can see how the infrared is being absorbed by the liquid, and so it's just a test kind of application to show you how long pass filters can work, and how you can start to image in the infrared with the long pass filter. So this is just a kind of a sample test that we did. As we move on, I mentioned acrylic filters. Now, the majority of filters are made typically with glass. We take glass and then apply a coating to them to create the filter. But acrylic is also a good option, and acrylic is a great option in situations where you can't have glass in the inspection areas. Maybe it's a food or drug inspection where you can't have glass, and you can use acrylic filters. Now, this is not a plastic kind of filter that you might be like a polycarbonate window or something. This is a cast acrylic with a very high optical quality. So you won't see the effects that you're used to with standard polycarbonate windows. Like when using a polarizer, you're not going to get this weird rainbow effect. And with other kind of plastic windows, you might have experience with the birefringence effect, where images are they look weird because of different refractive indexes. So the acrylic that I'm talking about here is a high quality optical grade acrylic. And again, this is a very beneficial because it's less expensive, it's easy to work with, and so custom shapes and sizes are very easy to be produced, and you can use them in visible and infrared imaging. You can also increase their robustness by adding different coatings, maybe an oleophobic or hydrophobic coating. This helps to reduce how that filter, how liquid might adhere to that filter. So if you're using acrylic as a enclosure window, as a protective window for your lens or your camera system, acrylic is a great option. And we'll talk about AR coatings in just a minute or two as well. But acrylic is a great option for protection, and also in situations where you can't use glass filters or glass components. Polarizers are a very commonly used filter in machine vision applications. You might know them to help reduce glare in your vision system applications. There's a few different kinds of polarizers. There's a standard linear visible polarizer, a visible linear polarizer. There's circular polarizers. Now, circular polarizers doesn't refer to the physical shape, but instead how it handles light. And these aren't typically used in machine vision applications again, but they're used in cameras that have an in-metering lighting system. And so it's designed to take into account that lighting system. And then we have wire grid polarizers. Wire grid polarizers are polarizers that have a microscopic wire grid that's embedded into them. These are the type of polarizers that you would use if the glare that you're seeing was caused by infrared light sources. These visible linear polarizers are really just meant for visible light, and they're made out of an iodine dye that helps to reduce that glare. So when you're choosing a polarizer, make sure you're aware of what type of light, what wavelengths of light are causing the glare. If it's a visible light source like a white, blue, red, green, then a linear polarizer will work fine. But if it's an infrared light source, like the one that I showed you with the long pass filter, this had a lot of glare in it, but we're using a wire grid polarizer to reduce that glare. You want to make sure that you choose the appropriate type of filter. Something else that you'll want to remember is when you're dealing with the polarizer, you want to polarize both your lens, which you might be used to, a polarizing filter for your lens, but then you also want to add polarizing film to your light source. This film comes in different shapes and sizes and can be custom cut to your light source, offered in film and glass, depending on the robustness that you need. But the important thing to remember is you have to polarize both. Polarizing one or the other is not going to effectively reduce that glare. So let's take a look at an application where polarizers really helped. This was an inspection of this particular beer label, and you can see it's highly reflective. It's hard to discern anything, and without a filter, it's almost impossible to read it. And then we add a polarizing filter to the lens. You can see there's not much difference between image 1 and image 2. And then in this third image, though, we add a polarizing filter to the lens like we did in the second image. And then we add some polarizing film to the light source. And you can see the drastic difference here between the first and second image and the third image. The glare is reduced quite well. And so keep in mind that when you're dealing with polarizers, you want to polarize both your lens and your light source for effective glare reduction. In this last image, I'm using additionally a red bandpass filter along with the polarizing filter. That's just to reduce some overhead glare, some glare that's being caused by some overhead lights. And so just stacking the polarizing filter with the red bandpass filter helps to just get rid of that glare. So polarizers are great for helping to reduce glare. Just remember to use filters and film on your light source. Neutral density filters, these we typically kind of call them sunglasses for your system. The filters that I've talked about so far, they really help you to increase transmission of your intended wavelength. Neutral density filters help to reduce transmission, usually because there's a lot of light. They help to reduce the light intensity. So if you have an application where maybe it's an outdoor application, there's too much sunlight saturating your image, or maybe you're looking at something like a welding application, and there's so much bloom that's saturating your image, and there's again too much light. Neutral density filters help to reduce that transmission and help to bring down that light intensity. Neutral density filters come in different optical densities, or ODs. So the higher the optical density, the less transmission. These are meant to be stacked together so that so that you can stack them together and increase the optical density, and thus decreasing the transmission. So neutral density filters are excellent for reducing the intensity of light sources. Multi-bandpass filters. Multi-bandpass filters are bandpass filters that have 2 or more wave pass bands. These are used in lots of different markets. They're used in intelligent traffic solution, surveillance, security applications, license plate recognition. And these are used in this kinds of applications because usually you're trying to image in 2 wavelength regions. You're trying to image in both the visible and the infrared, right? Like in a license plate recognition application where you're trying to read the license plate of a car, you might need to image during the day using natural sunlight, but then at night, you would want to click on an infrared light source to illuminate the license plate. And so typically how this is done is that there's 2 cameras, one for the day, one for the night, or there's a single camera with a filter that switches out mechanically. But these multi-bandpass filters are a single filter with 2 or more wavelengths. With in this particular one, there's 2 pass bands. So this pass band will pass your sunlight during the day and help you to illuminate your subject during the day. But then at night, when you have to click on your IR light, there's another band that will help you illuminate your subject in the evening. And these are also used for NDVI applications. Those are applications where you're looking at the vegetative health of crops. You can use these multi-bandpass, and we also have triple bandpass filters that help you, get data using software and in a standard kind of consumer level camera to look at different channels, visible and infrared channels, to see how healthy crops are. So that's another kind of use case for multi-bandpass filters. We'll talk about UV fluorescence imaging. Now, these types of applications, this is where we're trying to not image in the UV, so we're not looking at UV wavelengths. This is more for applications where you're using a UV light source to cause something to fluoresce. Maybe you're using a UV light to cause some kind of date code or some kind of grease to fluoresce. And while they're called UV fluorescence imaging, what you're really trying to image is still something visible, right? When you use a UV light to cause something to fluoresce, that fluorescing emission is now visible. And so that's what you're trying to capture. So in these types of applications, so far, especially with bandpass filters, you typically match your light source to your bandpass filter. So if you're using a red light for inspection, you get a red bandpass filter. A blue light for inspection, a blue bandpass filter. And so your first thought might be, okay, well, for UV fluorescence imaging, since I'm using a UV light, I should get a UV bandpass filter. While those exist, they're not meant to be used with these types of applications. What you want to do is actually use a bandpass filter that's capturing what's being emitted, what's being fluoresced. So here in this first image, I have this part that has some grease that will fluoresce when hit with the UV light. Without a filter, in the second image, it's hard to determine where that adhesive or that grease is. But in this third image, I'm using a blue bandpass filter. And what the blue bandpass filter, I'm using a blue bandpass filter because this emission, this fluorescence, was blue. And so what the blue bandpass filter is doing is blocking the UV light that's causing this glare, but capturing this weak emission. You can see this in the graph too. I have my UV excitation light source that's hitting this kind of a grease. It's causing it to fluoresce blue. And then I use a bandpass filter to capture that emission. So just remember, when you're using filters for UV fluorescence imaging, you care about the emission wavelength and not the excitation wavelength. So something important to remember. Let's take a quick look at a few different kinds of next generation applications that we're seeing using some different kinds of filters. This first application is a operator alertness system. It uses IR illumination to track eye movement of people who are driving. Now, this is a system that's mounted typically on a dashboard. It's projecting IR illumination to track eye movement of drivers, to keep them safe, really, to make sure they're not falling asleep, to make sure they're not looking on their cell phones. So these types of applications are, again, projecting infrared. And so it uses a filter, a bandpass filter, to block ambient light. And so that the IR illumination that's returning back into the sensor is not interfered with by other light sources in the car or that's coming in from the window. So this is a cool kind of application. And typically, we've been seeing these used in companies that are designing vehicles that are going into these big, dark mines. Drivers just going through these deep mines. But we're seeing this kind of trickle down into consumer cars as well. So if you have a car that kind of rumbles when the steering wheel shakes when you kind of doze off, this is the kind of technology that's being used. So it's kind of cool to see that. Another application that was really interesting was these self-navigating and collision avoiding drones. So these drones can navigate using a series of UV lights to communicate with each other and to help navigate. So they can really navigate in very dense environments. So it's not really using GPS, but instead they're talking to each other through UV lights. And also here we're using a filter to block ambient light so that the sensors can see the UV lights that are going back and forth. So another really cool kind of application. Another very popular and trending application is 3D laser metrology. The metrology is just the science of measurement, and they're using these metrology systems, lots of them using blue lasers, to take lots of precise measurements of different components so that they can be reproduced over and over again. This is very useful in, especially it's widely used in car manufacturing and machine manufacturing, where again they're checking these reproduced parts to make sure they fit within a very tight tolerance. And here also we're using a filter to block ambient wavelengths and to return this blue laser that's going back into the sensor. Yeah, filters are being used in all sorts of interesting ways, and they can also help in your kinds of applications. We're just gonna be wrapping up in the next few minutes, but I just want to point out a few things that you want to be looking for when you're selecting a filter. We just call these the key features, and you might not think that a filter is very important, but again, my hope today is to help you understand that filters are a necessity and not just an accessory. And so, you might have a very expensive camera, a great lens, wonderful lighting from our friend Daryl at Advanced Illumination, and you might have all that set, and you might realize you need a filter to help with this application. It doesn't make any sense to pick up a very poor performing filter because that's where the data is coming in. And so you want to look for these features. One of the features that you want to look for is wavelength control, how the passband behaves at different angles. Typically in a filter, a typical way that a filter is manufactured is, there's a glass and there's a coating applied to that glass, and that's what creates the passband. This passband is in charge of passing the wavelengths that you want to and blocking wavelengths that you don't want. Typically what happens in certain kinds of filters is that this passband, depending on what angle the light is coming in at, the angle of incidence or the AOI, this passband can actually start to shift. And so instead of passing wavelengths like you wanted to, when the passband starts to shift, it's passing wavelengths that are potentially going to be interfering in your application and blocking the wavelengths that you're using for illumination. So this is not good. What is going to result in a dark image or read errors. So you want to make sure that you select a filter that accounts for that shift, and actually a filter that where the passband doesn't shift. So the wavelength control is something that's very important. This is also important, not just when the wavelengths are coming in or light is coming in at a certain angle. This is also important because we're seeing more and more shorter focal length lenses that are being shipped to customers. And this is because machine vision applications are becoming more and more just contained, very tight spaces, and shorter focal length lenses allow you to look at a wider angle. But because of these wider angles, especially around the edges of the lens, when the angle is so steep, you're introducing much steeper angles. And if you have a filter where the passband shifts at those angles, again, you can be seeing some blocking instead of passing when you need it. So another reason to keep in mind why wavelength control is extremely important. The design of the passband is also very important. There's a couple of different ways the passband can be designed. One is like the flat top design, which is a very popular design method. The other way is a Gaussian or bell-shaped design. And we kind of lean towards the Gaussian or bell-shaped design just because it provides a better level of contrast. It's also very efficient at capturing LED output, because LEDs are being outputted in a Gaussian or bell-shaped output as well. And so we find the Gaussian passband the best way to capture all of that emission, but also blocking any ambient wavelengths that could cause some issues with contrast or just interfering wavelengths. So the design of the passband is important. Coatings, I mentioned coatings before, but a very important coating that you would want on your optical components and filters is the AR, or anti-reflection coating. This is very important because as light travels through glass or acrylic, there's some immediate reflection that happens. It happens naturally. So 100% of light doesn't go through glass. You actually lose 8 to 10% of glass, depending on the material and thickness. And so an AR coating helps to reduce that amount of light that's lost. So this is important, again, when you're using a filter to block ambient light, but to improve the efficiency of your intended inspection light source, you want to capture as much of that light as possible. And so an AR coating that's applied will help to reduce that loss of light that can potentially happen. This is just some different filters with different types of coating. This is a filter with no coating, no AR coating, I should say. You can see there's lots of light reflected. This is a coating with a single layer mag fluoride coating, which is widely used and a very good coating. But you can see that there's little bits of reflection here. And this last filter has a multi-layer broadband AR coating, which you can see there's almost no reflection. It almost looks like there's no filter there, but I assure you that there is. So anti-reflection coatings are very important to have on your optical components to increase and improve their efficiency. You also want to make sure that the glass that's being coated for your filters and other optical components are optically flat, rather. So they have near flawless surface quality. You don't want scratches and digs on your filter, again, because you're getting a very expensive lens, very nice camera, excellent lighting. It doesn't make sense to put a filter that's going to cause some distortion in your image and have some scratches or digs, again, that can show up in your image depending on where you put the filter. And also, you just want lots of different ways to be able to mount that filter, whether it's a threaded mount or mounting behind the camera, behind the lens in front of the sensor. Maybe it's for a lens without any threads or unmounted custom shapes and sizes. These are all things that you want to look for that, depending on the application, you're going to have to mount that filter some way. And so you want to look for some flexibility with that. Finally, one of the last questions, a question that I get all the time is, how do I know which filter to select? How do I know which bandpass filter or which short pass filter to select? We have, there's lots of different types of wavelengths that are being blocked and passed. How to determine which one? Well, the answer for that is to use a filter test kit. These are kits that have lots of filters, lots of different wavelengths, and bandpass filters, short pass filters, and this allows you to test with multiple ones, because the honest answer is there's not always, it's really hard to determine which filter exactly is going to work in your application because there's so many different variables. But a filter test kit, having that in your lab or having that with your engineers will really help determine which filter is going to provide you with the best results. So thank you for your time. Again, I want you to walk away with just understanding that filters are a necessity and not just an accessory. Thanks again for your time. My name is Georgy, again with MidWest Optical Systems, and hope you enjoy the presentation.